Great. Today Sabin will give his second lecture on Abelian Hall categories. So Sabin, go ahead.
All right, thanks. Let me know if there's problems with the sound or with the visual. Okay, so just to quickly recap, we're we have this stack which I denoted with a funny x, a, which is this moduli space um, where you're the so you have a quiver. I just try to here remind you all. You have a quiver that you start with, then you add loops, and there's a condition that the loops commute with the uh, with the quiver arrows, and that condition is depicted as a commutator relation, which is this SA notation. I'm not going to repeat the whole definition, and you mod it out by some gauge group, and it's the stack. So that's what we talked about last time, namely what the space is, and also what this group was, which was sort of the natural G product of GLNs acting on each vertex vector space across this torus, this two-dimensional torus. Okay, so what I'd like to sort of focus on today is explain how to get a T structure, how to describe a T structure on the derived category, which I just denote by co, of this x. I guess I wrote x like that. Yes. Okay. All right. So that's today's topic. So the procedure is done in 3 steps.
Hold on. You should remind me what properties of the T structure do you want, because otherwise Koch XA will be a T
Right.
structure.
Right. So we want a right. So there's the canonical T structure on here, but we want a T structure such that the convolution product we defined last time is T exact. Let me write it down. Such that convolution product is T exact. All right. So then, in other words, if you take something in the heart of the T structure on here and another object on XB, and you take the convolution products, then they stay in the heart.
Should it be Artinian category or not?
I mean, it will turn out to be Artinian,
Yeah.
but this is sort of fundamental property.
Yeah. Okay.
So we'll discuss the properties that it'll subsequently have. But in some sense, the key property that you want is this one, so that subsequently you get an abelian Hall category rather than just a derived Hall category. So in particular, the product should be for the yeah. So the product should be exact for the between the hearts of these T structures. Any other questions? All right. And I mean, we haven't done so many examples of products, but maybe we'll do it tomorrow. But it's pretty quickly you see that if you just take the standard T structure, then the convolution will not preserve it, will not preserve the heart. Okay, so the procedure is in sort of 3 steps. The first step um, is you start with the so I should say that this construction is actually essentially the same as the construction that Harold Willens and I did for the Coulomb the category associated to Coulomb branches. Um, and as I'll explain, the T structure is somehow something somewhat general, and it can be applied in that context, or it can be applied as more or less the same way in this context here. So what I'm describing here is just in some sense recapping this earlier work with Harold. So step one is you start with the with the with the with so remember these spaces, I can draw it here. This spaces map to, because this MA spaces map to the nilpotent cones, the product of the nilpotent cones mod GA hat. They are they are they are bundles. Well, the MAs are bundles over NA. NA is just a product of nilpotent cones. And this MASA is a derived intersection of two bundles over NA, and that's the critical structure that we'll be using. So the starting point, in fact, is here, and the idea is that we're going to try and lift some sort of T structure from here to here. So we begin with the T structure on NA, and of course you have the standard T structure on coherent sheaves on NA, but we don't want that. We want something that's T exact. And another natural structure is the structure of perverse coherent sheaves on here. So the step one is to start with um, so I guess they start with perverse coherent sheaves on on NA. And I guess when I say I guess G of A covariant perverse sheaves on here. So I guess I can write this. Okay. So as I'll quickly remind you what these are. I'm just going to quickly just go through the steps, and I'll illustrate it a little bit. Step two is to twist this T structure. So this is in particular, this gives you a T structure whose hard are perverse coherent sheaves on here. So I guess I mean start with this T structure, or with the perverse coherent T structure. The second step is to twist. So this is where the scaling C star acts. So recall the the scaling C star. Remember, there's inside of this two-dimensional torus, there's a scaling C star and a looped C star. The looped C star will not really play any role here. One can completely remove it. The scaling star will. Well, the scaling star in particular acts trivially on NA. That was part of its definition. And so if you look at C star covariant sheaves on NA, then then um, then they will this category of C star covariant sheaves will basically break up into blocks depending on how this C star acts, the weights with respect to which the C star acts. So what you're going to do is you're going to twist the standard T structure. So this is just a reminder, and we're going to twist this perverse coherent um, T structure, and I'll explain in a moment what I mean by that. So that so in the perverse T structure, um, we have well in the whole derived category we have this shift by one, which I think I briefly mentioned last time. There's this denotes the equivariant shift with respect to the scaling C star. So if for the perverse T structure, then for the usual perverse T structure, this shifting by this is T exact. But we don't want that. We want that the shifting by this, by 1 minus 1, become T exact. And this is a very elementary procedure, and I'll describe very briefly. And then last step, which is in some sense the most important one, because this is sort of either known or elementary, is the following one. So we're going to lift this twisted T structure. So I'm going to call this one the resulting T structure. I'm going to call it the causal perverse T structure. The reason I'm calling it causal is because this being T exact is reminiscent of a causal um, shift that shows up in causal duality, and also the source of the subsequent T structure is influenced by causal duality. So I'm going to refer to this twisted version of this guy as causal perverse T structure. So now lift a causal perverse T structure to all the way to XA. So those are the three steps. Um, all right. And to be more precise, I can be precise what I mean by this. So here's the precise statement, and then we'll sort of explain. We'll spend most of our time sort of explaining it. Remember, we have XA over there, so I'm not going to copy this definition. We have XA, and in particular, this embeds into MA um, mod G hat A by just this is an extra condition, so this is an inclusion here. I'll denote IA. Okay, and this is a bundle over NA, and we can consider the zero section of that bundle. I keep writing the GA, but the GA doesn't really play much of a role. Just to be precise, I'll keep it along. So we have NA mapping here by the zero section. So this is an inclusion, and this is the natural map. This is the zero section. Okay, and the claim, this is sort of what I mean by lift, is that there exists a unique T structure on upstairs on here, such that this composition, namely you push here and you pull back here, is T exact for the perverse coherent, for the causal perverse T structure on the base. Okay, so this is the sort of the key fact, which I'll try to explain where it comes from. Um, and is what exactly I mean by lifting. Okay. Um, then in particular, then the category, of course, we're interested in, which is what we started with, is just the heart. The Abelian category we're interested in is just the heart. HQ, the thing we started with at the beginning, I think I called it HQ, is the heart of this causal perversity structure. Staticity structure. And as you asked earlier, it has many of the properties that you would like, such that it is finite length in particular, and many other properties. But the point is that many of these properties that it has are former consequence via this lift of the corresponding properties that this category has. So it will turn out that this category is finite length, and as a consequence, so will this one. So will this one be. Um, okay. In particular, most natural properties I mean, I can't see all because obviously you can think of some weird ones, but most natural properties which this one has, whatever you start with, if you do this procedure, which works not just for this particular T structure, but more generally as well, we just want to apply it for this T structure, will be, so whatever property this one has, most of them will lift to this guy. Okay. Any questions about the plan, or can you still hear
Uh,
me?
yeah, I mean, step two, you really not want. I mean, you want some composition of two shifts to be T exact. So, is it a technical or it's why do you
Yeah, it's
want?
technical, and I'll explain why I want this.
Yeah.
It's I mean, yeah, it's if you don't do this, then you can still lift, but you won't get a T structure which is T exact for the
Mm,
composition.
okay.
And I'll explain why. So first, okay, I'm not going to go through the whole. Um, I'm going to try and fill in various details of these steps. Just let's say details. Okay. So for step one, um, let me say that there's this general theory of usual perverse sheaves, which perhaps you're somewhat, a lot of people are more familiar with. Um, and this is the analog of um, exactly the same theory applied to coherent sheaves. The nice things about nilpotent cones, of course, is that if you look at the action of GA without the hat, it doesn't matter. The action of GA, the orbits are all even dimensional. So you can take the perversity function, which is of half of the dimension of the orbit, is your perversity function. So when I say here perverse coherent sheaves, there's more than one category you can choose. It depends on the perversity function. So I should have said perverse coherent sheaves for the middle perversity function. Um, so one of the reasons why we switched to nilpotent, I mean, not one of the reason we switched to nilpotent cones early on to working over the locus where the the loops act nilpotently is exactly for this reason. Is because we want to use the category of perverse coherent sheaves on here with middle perversity. You wouldn't have to, but then you wouldn't. The convolution will not be exact if you didn't, if you use another perversity function. So I'm not going to go through the definition. I'll just say um, um, one just redoes the same definition as usual perverse sheaves. I'll just illustrate a little bit as some examples of perverse coherent sheaves because I think that's probably more um, instructive than to just give out the definition. But so let's see if Q is just 1 point, because anyway, in the case of NA in general is just a product of nilpotent cones. So we can just take the case of one nilpotent cone. So if you have this case, then N1 is a point, and that's not much to say there. The category of perverse coherent sheaves is just the usual category. And then N2 is a nilpotent cone. So it's a quadric, and so you have two orbits here. Um, you have the point orbit, 0, and you have, of course, everything else. And so one thing which is perverse is a structure sheaf of, I don't think I have a name for this guy. Let's say P. So you have so perverse coherent objects. In this case, just as some examples, of course, not all of them, but the simple ones at least. There's the structure sheaf of a point that's perverse, and then you have um, the structure sheaf of uh, the whole thing, and shifted by to make it perverse. There's a shift you have to include depending on the perversity function. The perversity function is half the dimension of the orbits. So because this orbit is two-dimensional, you shift by 1. So that's sort of the stereotypical example of of two perverse sheaves on here. And more generally, these are both simple. What other things you can do? You can take a line bundle or a vector bundle on this open orbit, and then there's going to be a unique extension, the intermediate extension. Um, you're going to get a simple perverse sheaf on the whole thing. So the theory in this case is very similar to the usual theory of perverse sheaves.
I'm sorry, what does the OP here? P is the zero orbit, and that's a single point. So OP is the structure shift of that point, or
Yeah, it's a structure shift of this point.
so that's a skyscraper
Skyscraper.
shift in this case, right?
That's a what?
Skyscraper
Yeah, it's a
shift.
skyscraper shift at this point.
Hmm.
Yeah.
And and everything is extended to, oh, I see. So the N2, that's an open, uh,
Yeah. So there's two orbits here.
yeah, the other one is open orbit, and you have a structure shift of the open orbits. And how do you view that as a complex of the shift on the, oh, it's the closure of the N2.
Sorry?
So
So this
here,
so
N2 is just the, that's basically, there are two orbits. N2 is the closure of the dense orbit. Am I
that's right. I
right?
mean there's two
Okay.
orbits.
Hmm.
There's the point and there's
Okay.
everything else. The closure of everything else is the whole thing.
Okay.
And the structure shift of the whole thing happens to be perverse in this case.
So basically, in general, if I have, in all the cases, there are only finite number of orbits. For each orbit, I take orbit closure, look at the structure shift of the orbit closure, and then
That will
go
be
and
that will
test
if you shift it by the half a dimension of the
half
orbit,
of the dimension of the
that
orbit.
will be perverse. Yes.
Okay, thank you. Mhm.
Yeah.
One more question about do you have an example of a perverse coherent sheaf that's not just concentrated in a single degree?
Uh, uh, I think it might be possible that could be saying something wrong because I haven't played around with them for a while. Um, Basically, oh, let me say it another way. So this has a natural resolution, an obvious resolution, by the by the cotangent bundle of P1 of -2, and if you take any line bundle upstairs and you push it forward, um, you're going to get a a perverse coherent sheaf. So it might not be simple, but it's perverse coherent. So if you take that line bundle to be like very negative over this point, over the P1, which gets contracted to a point, then you're going to get something which is not supported in just 1 degree.
All right, thank you.
Um, so that now it might not be simple, so I'm trying to think of it, but anyway. Um, so yeah, that's basically an example. Just take one of the simples that shows up. Any other questions? Yeah. Okay. So, but again, the moral to take away from here, more importantly, is that to each, not the moral, but the thing to sort of roughly take away is that to each, and I'll repeat this later a little bit, but to each vector button on the open, there's some extension of it, which gives you to any simple bundle on the open, there's some extension of it, which gives you perverse sheaves on the whole thing. Um, and particularly if you take the trivial line bundle, then that extension happens to be just the structure sheaf of the whole thing, and that's true more generally as well. But obviously there are other vector bundles, and they will not be as simple to describe explicitly. Just like with perverse sheaves, of course you can describe some perverse sheaves, some constructible perverse sheaves easily, but most of them are hard to describe. Okay, so that's a rough recap of the first step. The second step is, as I said, fairly elementary. What's the idea? This category chi if because the C star, I guess I could have written. Let me write it like this. This is GOA equivariant, right? In particular, there's the loop C star in here, which acts trivially. So this category breaks up, in fact, into sort of n into weight spaces indexed by the integers, um, depending on how the loop C star acts by what weight. So it's a direct sum decomposition to blocks indexed by n, and this shift by one takes you from block indexed by n to block indexed by n plus one. okay, or vice versa, depending on your conventions. But the point is that if you start with a T structure on the whole thing, and particularly have a T structure on each block, then what you can do is you can shift that. Whenever you have a T structure, you can shift it cohomologically up or down by one. You can just say it's the same T structure, just moved cohomologically down by one. So what you can do is you can shift this block index by n cohomologically, for example, by n. And then what will happen is originally shifting by one would take you from this block to the next one, and it was T exact for the original T structure. But now because you shifted them by 1, 2, 3, depending on what n is, shifting by let's say by -1 was T exact, shifting by this much is going to be, you shift it so that shifting by this much is going to be T exact now. Okay, so you shift, let's say you shift the whatever T structure you started with, in this case the perverse T structure, by the appropriate amounts, I guess by n on the nth weight space, so that this shift becomes T exact. Okay? Maybe minus n, whatever your convention is, depending on what's plus or minus. But this notational wise, you want this thing to become to be T exact. Okay? That's all there is, and it has nothing to do with perverse coherent sheaves. You can do this for any T structure. We just do this twist. And again, it's not clear why you want to do this, but I'll sort of explain later on when we get to the third step. Okay, well, we are at this third step. All right. Let's see. Anything else to say? Okay, so for the first step, I'm going to sort of try to explain the general theory that allows you to do this, to get this claim, which I'll call causal T structures. Okay, so the idea is, as I mentioned, the spaces we're interested in are the derived intersection of two vector bundles inside of third. So that's the setup in which we're going to be working. So we're going to have two vector bundles, v1 and v2 inside of W over some base x. So this is your base, and these are vector bundles. And as usual, you can have some sort of group action floating around that's equivariant. It won't play much of a role. So I'm going to ignore it for the discussion here, but it just comes along for the ride. I'm going to ignore it here because it doesn't play any role. And but what does play a role, of course, is the scaling C star. So the setup is that we have these vector bundles, and C star acts trivially on X and weight 1 on the fibers of W.
This is a scaling C star.
This is the scaling C star.
Thank you.
It's supposed to be exactly our earlier scaling C star, but I'm just thinking of it as a general situation where this is the input that you need. Okay, that's the setup. And the space we're interested in is the intersection of these two vector bundles inside of W, namely the derived intersection. So we have, let's say, V1 and V2 mapped to W, because usually I like to write it V1 here. So let's do that. This is V1 and V2 mapped to W, and this is a derived intersection of these two. So I'll use this notation. So this is supposed to be our are MASA, where these two are just the same. They are MA, and this W is MA cross MA. Okay, so that's the setup. And so just like we had earlier, I'll give these guys names. Let's say I1 and I2. We have the following. Well, we have the following. We have I1 maps to V1, and then you have sigma 1, let's say, which is the zero section of X. We map from X to V1, which is zero section, and we similarly have one for I2. You can choose either to work with. And the statement is the following. So, theorem. Given a causal T structure on the derived category of T-star covariant sheaves on the base. So this causal means it's in the terminology used earlier. It means basically that this guy is T exact. So I guess I should be more careful in to describe this. So what a causal T structure is, I think I skipped somewhere. Definition. So I'll just try to squeeze it in here. Maybe I'll remove this for a second and I'll try to squeeze it. So what a causal T structure on the base is a T structure such that tensoring by any so there's more I'm saying. It's like this. Tensoring by any vector bundle that's has weight 0 with respect to the T star is T exact. So this is T exact. For any, this is a vector bundle on X. Okay, so tensoring by any vector bundle is T exact. So, for example, the standard T structure would be an example. Obviously, tensoring by vector bundle is T exact. The perverse coherent T structure is also T exact when you tensor by a vector bundle. That just comes easily from the definition. Such T exact structures are sometimes called local T structures. Okay, so it's a local T structures such that, in other words, such that this is T exact, and shifting by 1 minus 1 is T exact. So both of these are T exact. So that's what I want to. My starting point is that T exact is a causal T structure on the base. In particular, if you start with any local T structure, you can always twist it like we just did to get a causal T structure. So there's lots of such things, including the standard T structure. It's just not what we want to start with. All right, so you start with a causal T structure, and namely any T structure satisfying this property. So let me be precise. Weight 0 vector bundle on here. Obviously, you can shift the vector bundle by. Notice that if this is T exact, then shifting by the covariant parameter is no longer T exact, right? Because if it was, then also shifting by cohomologically would be a T exact, which is no good. So obviously, I need to put some condition on V and what weight it has. So if it has weight 0 vector bundle, then it should be T exact. Okay, so you start with a causal T structure on here. Then there exists a unique T structure on Y, determined by let's say such that it was determined by the fact that the composition. So I just erased it, but the composition I1 lower star sigma 1 upper star is T exact. And just to remind you again what this is I1 here, and so you have Y maps to V1, and X is the zero section, like so. Okay, So in other words, if you push forward here and then restrict to the zero section, you want that to be T-exact. And the claim is that there exists a unique T-structure on here determined by this condition, namely this composition being T-exact. And that's, of course, the T-structure we considered earlier, where Y was XA and so on. And X was NA.
Is the sigma 1 the zero section?
That's right. Sigma 1 is the zero section. Yeah.
Thank you.
Yeah. Okay. So that's the theorem. So I think it's worth saying some words about where it comes from and what are the main ideas. Okay. And as I mentioned earlier, most of the properties, I can't say all of them, but most of the standard properties which this T structure has will be inherited by the corresponding T structure on Y. All right, so let's do some examples of this result, and then you'll also see why why this weird causal shift shows up. Okay. Let's do some examples. So the first examples I'm gonna do, because in some sense what this is really doing is it's gluing together some sort of T structure on the base X, which in principle could be an arbitrary space, doesn't have to be linear, with some sort of T structure on the fibers. In particular, of course, we can take X to be a point, and this discussion is still a little bit interesting. It's still interesting, and what this is doing is somehow gluing together, in some sense, T structure on vector spaces with some sort of T structure on the base. So a not so stupid thing to consider is just X of a point and see what happens. So the very, very simplest thing to do is to take V1 and V2 and W to be all the same. So V1 equals V2 equals W. Okay. And then Y, of course, is just it's just a vector space V. It's just a vector space W. So, okay. And let's take this to be one-dimensional as well. We could do this more for more higher dimensions, but it's not really that much more enlightening. So let's do it to be one-dimensional. So this is one-dimensional. Okay. So it's a very silly thing. So you can consider this. You start with the standard, well, on a point, and it's not really any interesting T structures. Even T structure covariantly, you start with the standard T structure. You twist it in this way to get a causal T structure on C star covariant sheaves on a point. And then you lift it, and you get a T structure on this guy. Okay. So this C star acts just by scaling C. Pretty simple thing. And what are some objects in this heart? So let's denote the heart by putting a little heart there. So this is let's say this is the heart of the resulting causal T structure. So the T structure you get as a result, I'm also calling it causal, obviously, for obvious reasons. So what does this contain? Well, it contains the following objects. It contains the structure sheaf of C, that's in the heart, and shifting by this amount is also T exact. So it'll contain any object of this form. Okay. And what else does it contain? It also contains the structure sheaf of the origin. In this case, there's two orbits. So in terms of what kind of objects can you get? Well, you can get the structure sheaf of the whole thing or the structure sheaf of the origin. And It's sort of natural occurring objects. And this guy is also in the heart. And of course, you can also shift it by any amount and it's going to stay in the heart. Okay? And this T structure is going to be,
Here, I'm get a bit of confused. This time the C is what you're computing here. C is the Y as in the theorem, right?
yeah, this is your Y, yeah.
And so the X in this time is the point.
Yeah, X
So
is just a point.
So the sigma 1 star,
Yeah.
so that one is exact. So can we see that sigma
Yeah,
1 upper
so
star, I1 lower
yeah,
star?
so you have let's see, you have Y, we said I1 into V1 and sigma 1, right? So this is a point, this is C, this is C, this is the identity, and this is just 0. Okay? It's just a 0 section, right? So it's just the point going to 0. Is that what you're asking?
Yeah, I want to see the functor is exact. So what the right hand side on
Ah,
the
right. You want to see the function is exact, right? So,
yes.
for example, yeah. So note that's what you're asking. I didn't understand. So let's apply this to one of these objects. If you apply it to this object, it's pretty clear what happens, right? Well, let's do it. So you do this. You do I1 lower star I1 sigma 1 upper star of O of C. You're pushing it forward, so you just get O of C, and then you're restricting it. So that's just O of the point. Okay, right? And on the other hand, if you do of this guy, and the same thing with the shifts, you get a shift, but remember the shift is T exact for the causal T structure on a point, so that's okay. And then for this guy, you push it forward, you get of 0 in here, obviously, because it's just the identity. And then to pull it back via this map, you have to resolve this. So you get the resolution of this is O of C mapping by multiplication by whatever your variable is there, say spec of x, C of x is multiplication by x. And that's your resolution. And there's a shift of -1 here because x has degree 1. Okay? Of course, it's convention, but my convention is that this is a -1 here. If it had been a 1 here, then I would, because of the convention, then I would have redone my whole thing so that so that 1, 1 is T exact. So this is just a convention thing. So, so you get this, and of course, when you pull it back, you get everything splits. So you get O of O -1 mapping to O of I guess point is what we're calling it, point, right? Which is just this is in degree 0, so this is O of a point. Direct sum. This is in degree -1, so this is O of a point shifted by 1 -1. Okay. So there you go. This is in the heart. And now you're seeing exactly why you wanted this shift to be T exact. It's exactly because of this reason. And that's essentially it. Any example I would be doing would just be of this sort, would be just taking this very, very baby example and just doing it slightly more general. So these resolutions would be more general, but the principle would be precisely the same.
Thank you. Because the C star acting on the point trivially. So each of this the coherent shifts becomes vector spaces, but they are representations of C stars.
Yeah, so on a point, we're just talking about representation of C star, right? So all the objects are just irreducible representation of C star. Sorry, all the objects are representations of C star. The simples are just characters of C star, and we're shifting the standard T structure so that if you have a character of weight 1, then if you shift it down by one,
It's also shifted, and the weight also shifted.
exactly, yeah.
Yeah, that's a good example. Thank you.
Okay, let's see what else to say. Yeah, so that explains why the 1 minus 1 has to show up. And one thing to note is interesting about this heart is that it's finite length. The usual heart on C, of course, is not finite length. So let's sort of get an idea of why it is finite length. In particular, if you look at these objects, this one is simple. It's a simple object, but this one is not simple. In fact, up to shifts of this sort, there's only one simple object on here. It'll be just a structure sheaf. So to see that and sort of what happens, namely why is this one simple and why it's finite length, just a node almost. So note, if you start with this standard exact sequence that we already see this, right? You have an exact triangle in the derived category, which looks like this, right? And of course, you can rewrite this as as OC mapping to OO mapping to OC shifted by 1 minus 1. That's an exact triangle in the derived category. And this triangle is an exact sequence inside the heart. This is a short exact sequence in the derived category in the heart of this guy. Okay. So there's your simple, there's another simple, and this is an extension of this with this guy. And this kind of explains, at least intuitively, what's happening and why it's finite length, because the main reason why the standard T structure is not finite length is because you have this guy, you have this as a sub, and so on. And so it keeps going, right? So it's not a finite length category. But once you do in this T structure, this guy is no longer in the heart. So you cannot do that. In fact, this guy is simple in the heart of this causal T structure. Okay. So that's maybe, even though it's such a baby example, it captures a lot of the essence of what's happening. Of course, there's more details, so I'll try to fill in a little bit more, but this is almost the most important case. Let's do sort of another extreme case. So this is the case when v1 is equal to v2 is w. Let's do the case when x is a point. v1 and v2 are zero dimensional, and w is one dimensional. Okay. Oops, not w2, just w. So in this case, this is the self-intersection of 0 inside of C. So I sort of mentioned this last time, but y in this case is spec of C epsilon mod epsilon square, where the homological degree of epsilon is -1. So this is a derived, a zero-dimensional derived scheme. All right, so that's the space we're looking at. And whenever you have a derived scheme, you can always look at the classical locus. This is CL stands for classical, and it's a sub scheme. And this is completely analogous to how if you have a non-reduced scheme, you can look at the reduced subscheme. This is the analogous reduced subscheme. So you always have the classical locus occurring as a reduced, not as reduced, but as a subscheme. And of course, the classical locus in here, the classical subscheme in here is just spec C, where you get rid of the non-reduced part. Okay. So that's the picture here. And if you look at, that's what Y is. And if you look at the heart of the T structure in here, what does it contain? Contains, just like sort of earlier, what's in here. What you see, you have the structure sheaf of the whole thing. So of y is in there. Okay, and of course you can shift it by anything you want. Goes without saying. And something else which is in there is just like this is a subscheme, so you can push this forward, right? So you have I'll just write O of y classical. It's a push forward of this. Do I want to call it a name? I'll just leave it like that. So O of y classical, the push forward, is also in the heart. Okay, and this is also a finite length category, which is less surprising now because it's C epsilon mod epsilon squared, and there's an analogous short exact sequence that looks like that. So in here, one has an exact triangle, which looks like the following. You can take the structure sheaf of the whole thing, so O of y, and then there's a map to the structure sheaf of the reduced thing, right? There's always such a map, it's just formal nonsense. And then, because this is C epsilon and epsilon squared, it's basically two copies of C, which is each copy kind of looks like this. There's there's also something left over here, which is O of y classical, but we have to keep track of this is in degree, this is times epsilon, right? And epsilon has degree, homological degree -1, so it's shifted by 1. And it also has, I didn't specify, but because of the C star action, if you do it carefully and you identify this thing carefully when you write the fiber product diagram, it has a shift by -1 as well, equivariantly. Okay, so the epsilon has homological degree -1 and scaling degree, if you want, 1. So you get this. And this is also a short exact sequence in the heart. There's no longer you don't have to move it over or anything. It's just short exact sequence in the heart. And in this case, this guy is no longer simple, and this guy is simple. So here's your simple. There's another simple, and that's an extension. And it's completely analogous to what's happening on this side. And it's not just by coincidence that it's analogous. In fact, there's a duality, a causal duality between these two sides, whereas an equivalence of categories between these two sides, which takes this guy to O of y and this one to that. So I guess this one to that. So there's a causal duality happening here, which is part of the reason this is all we're calling this causal T-structure. Okay, so this is sort of the other extreme, and the two extremes are kind of related by causal duality and therefore look quite similar. And you can see now the importance of this derived structure. I guess if you hadn't been derived, then this would be your space, and of course you wouldn't be able to see very much. But certainly it would just be spec of C. You wouldn't look similar to that one. Okay, so those are the simplest but most important two examples. And if you combine them, let me just say, right, because what's the most general thing you can say at the level of vector spaces? So if you combine these two examples, so more generally, let's take, let's take x to be a point. Then, let's see, you can say you have co-C star of V1 W V2, the fiber product, the derived fiber product. And what is it going to look like? Well, let's just say, I'm trying to think how much I can say in argument notation. Let's just say this has up to shifts by this, obviously, because you can always shift, has a unique symbol. One symbol, the heart, has one symbol, which is O of y classical. This is y. I should have just said y. This is y, right? So if you look at the classical locus, which in this case agreed with y, in this case obviously didn't agree, was smaller. But if you look at the classical locus in here, that's a vector space. This is an intersection of two vector spaces. So it's a vector space. The structure sheaf of a vector space, I thought of as a sheaf on this derived intersection, is this symbol. And it's a unique symbol up to these causal shifts. Okay, so that's kind of the picture that generalizes, and so the general picture is quite similar to, in the case when x is a point, is quite similar to what we saw in these two examples. Namely, there's only one symbol and everything is obtained by extending. Any questions? Just gonna get a sip of tea. Okay, that's a good place to stop.
Well, if you want to stop, then I will ask you for one more example, but maybe.
I was just gonna say what the main tools are
Okay, go ahead.
for proving something like this. And then maybe I'll do your example, and that's probably a good time to stop. What do you think?
Yeah, fine.
So the main tools, at least I'm not gonna go into all the details, but the main point I want to get across is they're in some sense fairly formal. Let me say it like this. Let me say it like this. So the idea is, suppose you have two categories. So these categories you think of them being derived categories, what are often called infinity categories. And they should be representable. And what representable means basically is that co-limits exist. So co-limits means direct limits. So in particular, direct sums should exist, arbitrary direct sums. So these are large categories. So suppose you have two large categories and you have two functors between them. One being the adjoint of the right adjoint of the other. This is the right adjoint functor. Okay. So the statement is that if you have a T structure on D, okay, and phi r is left T exact for this T structure. So this means if you do this composed with that, well, it's left T exact. Then there exists T structure, a unique T structure. Obviously, it's unique, given what I'm going to say. On here, given by C less than 0 is the pre-image of D less than or equal to 0. And such that phi is in fact completely T exact. So let's recap. Under some very general, assuming these are large categories, then if you have an adjoint pair and the composition is left T exact, then you can define a T structure on here such that the less than or equal to 0 part is just a pre-image of all the objects. The C less than or equal to 0 here are all objects whose image in here is in D less than or equal to 0, and then phi is T exact as well. So the functor is T exact for the new T structure defined this way. Okay, so anyway, this is sort of a very a general fact, which kind of comes down to the fact that in these giant categories, you can kind of define there's lots of T structure. You just need to basically define this to be whatever category you want, and you can more or less always extend it to a T structure. So there's this very general formalisms for at least on large categories, for example, of quasi-coherent sheaves, of taking a T structure in one category and obtaining from it a T structure in another category. And the idea is, how does this relate to what we're doing here? The idea is, for example, to look at this functor. I guess I called it I1. So the idea is, let's see, to look at, just give me 1 second. So yeah, cove storm x. I think it's pi upper star. Like that. But we can just focus on this part. So the idea is you want to lift the T structure from here to here, from here to here. And the idea is to look at the functor of push forward by the projection map, like pi is a projection map. And well, let me forget about this. Let's just focus on this one. So you have I upper star, you have I1, sorry, and you have I1 lower star, and in the other direction you have I1 upper shriek is the right adjoint. And the idea is to apply this result here. And of course, if you wanted to apply it, you need to go to representable categories, so you need to shift to quasi-coherent sheaves. That's okay. But apply the result here to take your T structures. So you suppose you already lifted a T structure from here to here, which you can use a similar technique. Just give you an idea of how it works. Then you can also you also lift it from here to here by applying the result, this result, and showing the resulting T structure, which is a priori in this large category, restricts to the smaller one we're interested in. Okay. So that's a general idea that you can define somehow T structures much more easily on large categories, and then if that's the way you approach things, then the hard work is to actually show that, in principle, the harder work is to show that it restricts to your smaller category you might be interested in. And in this case, at least for this one, it's actually pretty easy to see that the induced T structure here restricts. And it's also fairly easy to show that this is left T exact and so on. So of course, there's a bunch of details to fill in, but it's just an application of this concept with a little bit, with the hard part, in fact, checking this second part that it restricts to the finite, to the subcategory of coherent sheaves.
Probably you said I didn't get it. So in this case, the T structure on V1 is that just a standard T structure from the complex?
Sorry, can you repeat the question?
Here to apply the general main tool. So you you have a T structure on the cohesive star of V1. So
Yeah.
what is the T structure on that?
Yeah, so you're right. So that one you get from a T structure on X, which this is the one you start with. And
Uh-huh.
the two functors here are pi lower
Also,
star
mhm.
and give
And
me
the
a sec
zero.
first. And yeah, at least I don't want it's not affine, but well okay, let's say like this. It's pi, uh it's sigma one upper star and
Mhm.
it's right out drawing whatever it is, sigma one, I guess
So
lower star.
one of the Android pairs with X. Okay.
Yeah.
Yeah, that's
So you
clear.
start from X and you lift it to here using these guys, and then you lift it here.
Really good.
Yeah.
Okay.
So in fact, if you actually trace roll this, there's only one hard step, which is showing that if you do it here, the resulting T structure restricts to the coherent subcategory for this one. That's the hardest one, in fact. Going from here to here, showing that it restricts. Showing that it restricts here is actually easy. So yeah, for
Thank
whatever
you.
it's worth. It's all fairly goes through fairly easily. There's only um, one hiccup there.
And in your work with Williams, you also used this general effect for affine Grassmannians. I mean,
That's right. It's the same idea for it. The T structure here is right. So in the case of sorry, you're asking about the Coulomb branch situation?
yes.
Yeah, the Coulomb branch situation is similar. So in this case, let's see. In this case, you have x is an a. V1 is equal to V2 is equal to MA, and Y is this MASA. And in the Coulomb branch situation, X would be the affine Grassmannian. V1 would be something like the affine Grassmannian cross NO, and V2 would be this twisted affine Grassmannian cross NO, sometimes written TO, and if you're familiar with the with the notation. Oh yeah, and here W is just a product of MA over NA MA. And here W would be GERG cross NK. So in the case of the Coulomb branch situation, W is a trivial, of course everything is infinite dimensional there. The W is a trivial bundle. V1 is trivial, V2 is not that it matters for the theory. And in this case, it's a little bit slightly different, but same idea.
Did you say the bottom part was a column branch, right?
Yeah, so the Y is what is the fiber product of this with this over
Yes.
that
Yeah.
is what's usually called this R space in the
Yeah.
literature. Yeah.
So
At least the classical part is what's usually called the R space, but classic.
yeah. So
We
this
call
is
this R, but in the original formulation of a BFN, this space was the classical part because they didn't consider the derived structure.
so this is local case. You said the column branch, and the
Yeah,
top
so the category, the
example
Coulomb. So
was
if you look at coherent sheaves
hmm
on this Y, equivariant with respect to whatever the corresponding groups are, which is like G of
Yeah.
O,
hmm
then the K. This is the category whose K theory is
Okay.
the.
Okay. Thank
I
you.
mean, I mean spec.
All right. And the example I wanted to ask you some time ago, it's a Jordan quiver.
Yeah.
When I believe that your commutation relations give you what is known as commuting variety or something like that.
Yep. That's right.
Uh, yeah, since, well, I was interested in it long ago, but you have this T structure, which, so it's Artinian, so you have, I think, finitely many simple objects, and they are parameterized by what?
Hmm. Okay, good question. So I didn't get to it, but I was going to say it. So fact, um, simple objects and more generally in co C star Y heart are in bijection with simple objects in co C star X heart. So they're in bijection. So we saw this in the case X is a point, right? I told you at some point there's only one simple object up to shift and Y in that case, right?
Yeah.
Oh, it's right there, right? So in that case, there's only one simple up to shift, and likewise on a point, there's only one simple up to shift. But this is true more generally. So in the case of quite generally, so corollary of this is that simple objects in co XA are in bijection with simple objects in co NA mod GA. Okay? So and these ones are in bijection with pairs of O lambda and V, where O lambda is an orbit and V is an irreducible vector bundle on O lambda. Since it's an orbit, the derived category is, I mean, the category is equivalent to the category representations of the stabilizer, so some subgroup, and for any irreducible representation of that subgroup, you get a reducible vector bundle. So the simples are in bijection with such data.
Mm-hmm. Oh, okay, great.
So in the case, yeah, I can try to make this more explicit in the case of Jordan quiver, if you're interested. Maybe I'll do that next time.
Yeah, maybe next time. Yeah, it's interesting.
Yeah.
Yeah,
But
I
the point is
mean,
that somehow the simples in the case of Jordan quivers are naturally indexed by the same as the simples in the case of just the usual. I mean the one vertex quiver
yeah,
with
yeah.
no.
Okay, good.
But I'll try and do some examples in the
Yeah,
case
sure,
of the Jordan
sure,
quiver if you're
sure.
interested.
People like quivers here.
Yeah, I'll try to describe some simples, and
Yeah,
some and what as far as I know what the most general statements are.
yeah. Okay. More questions? Uh, okay. And so our matrices will be tomorrow. Yeah.
Yeah, so I'll do. I'll say something about R matrices, and I'll say something. I'll try and do examples, particularly the Jordan quiver one.
Okay, great. Okay. Well, thank you very much. Yeah.
All right.
Okay. So then this is it for today. Yeah.
Okay. See
And
you
see you
tomorrow.
tomorrow.
Bye.